In 1972, astronomers Carl Sagan and George Mullen pointed out a seeming paradox in planetary science regarding Earth. Early in Earth's history, it must have had liquid water, or life on Earth could not have arisen. But there was a problem. Stellar evolution is such that the Sun has slowly and steadily increased in luminosity across its lifetime, and will continue to do so until it bakes Earth. And at the time early Earth first had liquid water, the Sun was only 70% as bright as it is today. In short, the paradox shows that Earth should have been frozen solid. It should not have had liquid water and should not have had early life, yet there is evidence that it did. There have been many solutions raised as to what happened in those days, and they have ranged from changes in Earth's albedo, astrophysical reasons, and so on, but the main favored theory is that the greenhouse gas carbon dioxide was present in much greater concentrations to hold in heat earlier than we had previously thought. The problem is there was no evidence of this either way. We simply did not know exactly what Earth's atmospheric composition was back then, and we had no indicators for how to even characterize the atmosphere at that period. This has now changed, tentatively at least, and it may represent the final answer to the faint young sun paradox. The story is this. Jared Landry, an astrobiology PhD student at Tokyo's Earth Life Sciences Institute, analyzed lunar samples taken by the Apollo missions for evidence of what Earth's early atmosphere looked like. This involves a period of Earth's history that is frankly an enigma, the Archean period. This is the second oldest of Earth's 4 geologic eons and represents the period between roughly 4 billion years ago and 2.5 billion years ago. During the beginning of this period, the late heavy bombardment was still going on, and Earth was still being hit by large amounts of impacts. We have very little information on this time as most evidence is gone, and the period before it, the Hadean, is only represented by rare zircon crystals. So the picture here is really incomplete because everything about Earth weathers, subducts, melts, changes over time, including the atmosphere. There is some evidence that a glaciation period did occur during the middle of the Archean, interestingly, and there was continental crust present at the time. But the majority of land on Earth was still under oceans at this time. We know that Earth's atmosphere during the Archean was methane-rich and had very little oxygen. But the earliest life started during this period as evidenced by stromatolites, which are primitive microbial mats, with photosynthesis showing up about the middle to late Archean along with other processes, which started a slow process of dramatically transforming the atmosphere into something we would more easily recognize from our point of view today. There have been studies over the years that suggest that Earth basically sneezes evidence of its atmosphere onto the surface of the Moon, and it might be detectable, even this long later from this period. The Moon is close, and the Earth's atmospheric gases get ionized in the upper reaches of the atmosphere before being redeposited on the surface of the Moon by the solar wind. As a result, evidence might have been left that could give us a historical profile of Earth's atmosphere, at least of sorts. This presents a challenge in that this process forms what effectively is an outflow channel that the Moon spends a short amount of time inside during each orbit. But that also determines how much of this residual material would be present in lunar samples. The work focused on a period during the Archean about 3.5 billion years ago, about the time life arose, which again is a time where we simply don't know enough about the atmosphere at the time to determine what effects that had on things like environment, what was going on the surface, and even some aspects of chemistry involved in life that were influenced by atmospheric composition. This is one of the major problems in determining how abiogenesis occurred. And indeed, even experiments like the famous Miller-Urey experiment where amino acids were produced from chemical building blocks under the conditions of early Earth were based on approximations that today we know aren't entirely accurate. The result of the examination of the lunar samples shows that Earth's atmosphere was much more sulfur-rich during this period. This was unexpected, but in a way answers a question. Sulfur is a component necessary for life in complex chemistry, and if that atmospheric sulfur were enriching the oceans, then that solves a peripheral mystery. But there's a much bigger discovery here, and it potentially collapses the faint young sun paradox. It turns out Earth had 100 times more carbon dioxide in the atmosphere than it does today, which is just barely enough for a robust greenhouse effect, which would have kept the surface warm for liquid water despite the sun being significantly less luminous. Interestingly, the concentrations of carbon dioxide found were just about in line with estimates on how much carbon dioxide would have been required to keep Earth's surface warm. Slightly less, in fact, but not drastically so. This was actually really tricky work in that a bunch of different factors had to be accounted for, ranging from estimating the amount of micrometeoroids that were hitting the moon to the effects of the solar wind, which incidentally deposits material on the moon as well, in the form of the infamous helium-3 in the regolith, that is one of the major potential resources present on the moon, especially if that turns out to be key for fusion energy. Regardless, it's important anyway since Earth is starting to run low on helium. It's effectively non-renewable on short timescales, and we use it in all sorts of industrial and scientific capacities. So a second close source of helium may prove important in the future. After eliminating all sources other than Earth for material depositing on the moon, the reasoning was that what's left behind must have come from Earth. Found was the expected levels of methane, itself a greenhouse gas. The presence of the methane might have been what put the equation over the top and into the expected greenhouse gas ability needed to insulate Earth. But it does create another mystery, and it's the sulfur again. It's actually hard to maintain that much sulfur in the atmosphere of the Earth. The ocean readily absorbs it, and it certainly isn't doing that now. So whatever was doing it and replenishing it is no longer happening today. It's difficult to say what that means because low activity with the water can do it, or just a cool environment, which either is possible in this regard because while Earth may have had liquid water oceans, we don't know how cold it was above freezing. There's actually an unusual tidbit in this story. So there have been 3 countries to return samples from the lunar surface. The United States famously, but also the Soviets and China have done it as well. But it wasn't until 2024 that someone actually returned a sample from the far side of the moon. All of the other samples are from the near side, which doesn't have an effect on this particular study because the near side is where the deposition from the atmosphere occurs. But yes, China sent a mission in 2024 and became the first country to return a sample of the far side. There are also quite a few known meteorites that originated on the moon, but those are problematic in that we don't know from where on the moon they originated, and very likely it was a mixed bag of all sorts of different places. One interesting aspect of abiogenesis research is that once we know how it happened and the conditions it happened under, we can then apply those ideas to looking at Mars or the ice shell moons to determine if they had similar conditions. Interestingly, Earth no longer does. The oxygenated atmosphere we have now is not the same by any stretch as the atmosphere that life first arose in on this planet. If indeed life did arise on this planet and was not deposited here from somewhere else. But today's atmosphere is deadly poisonous to the first life Earth had. It retreated deep below the Earth in anoxic environments. So it may actually be the case that abiogenesis cannot occur here at all any longer, since the chemical conditions for it no longer exist here. This opens up a Fermi paradox question, since we don't know the exact conditions of Earth's atmosphere during the Archean. Though this work gives us a large step forward, we don't know how common that situation would be. And if abiogenesis requires very tight parameters in a different atmosphere than we have right now, that could make life very conditional, and thus very likely rare. Even more rarely, it might evolve complexity, and rarer still, intelligence. But the numbers still overwhelm this. Even if all great filter steps are hard, that still leaves room for the universe to be peppered with millions or more civilizations. So rare is a relative term here. So this might finally resolve Sagan's faint young sun paradox, but it also creates more questions. That paradox also affects Venus and Mars. They too orbited the faint young sun, which would put Venus well within the early sun's habitable zone. And it may also have been a very different planet with very different conditions, and in some models could have supported liquid water for a time, before the increasingly luminous sun drove its habitable zone out past Venus. But the estimates for the inner edge of the habitable zone during the Archean, which it would have moved outward across that eon, was 0.70 AU distant from the sun. Venus is 0.72 AU distant from the Sun, so Venus would have been better off back then. Mars would not. Mars would have been subject to much less solar radiation, but we also know that Mars also had a thick carbon dioxide-dominated atmosphere at the time, and might have also supported a significant greenhouse effect of its own. And we know there was liquid water acting there for a very long time. The conditions for that remain unclear, so maybe the faint young sun paradox might be solved for Earth, but maybe it then becomes a paradox regarding Mars. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently wondering what else the moon is hiding. You know, every time Earth got impacted in the early days, it was possible for material to get ejected from Earth to land on the moon. I think it would be interesting, and potentially likely, that the oldest rocks from Earth we end up with actually were blown off and deposited on the moon, and might come to light with further exploration. Interesting, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations of the interesting, weird, and unknown aspects of this amazing universe in which we live.